Good morning and thank you for the introduction. The risks and damages associated with coastal floodings are a large concern of low-lying countries with extensive nursery areas. And the impacts of severe flooding events include loss of infrastructure, extensive coastal erosion, loss of land, and even loss of life. The modeled annual maxima in the eastern Baltic Sea has shown a remarkable increase, and the increase has been the highest in the eastern Gulf of Finland and in the Gulf of Riga. And this pattern leads to the question, what is behind this kind of increase of extremes, and is this pattern going to continue, and how it will be spatially distributed? The local water level in the Baltic Sea is a combination of joint impact of several drivers that follow different probability distribution, and the presence of various distributions generates different levels of exposedness and vulnerability for low-lying coastal areas regarding to extreme water levels and their return periods, and a longshore variation of the shape parameter of generalized extreme value distribution may prove itself as a helpful tool for classifying the coastal segments by the likelihood of experiencing higher extreme water levels. To explore this, we used modeled and observed water levels. Two sets of modeled water level data are extracted. First is extracted from the Rossby Central Ocean model, and this temporal resolution of this is 6 hours, and this covers years 61 to 2005. Second set of model data is extracted from the RCA4 NEMO, and it has temporal resolution of 1 hour, and it covers years 61 to 2009. And they both have spatial resolution of 2 nautical miles. And we cover, our study area is shoreline of Lithuania, Latvia, and Estonia. Altogether, it covers 351 grid points. And model data we complement with the observations from 14 sites along the study area. To estimate the extreme value parameters of water level maxima, we used the largest value that occurred during the calendar year. And this, in the conditions of Baltic Sea, these values may be correlated to the impact of clusters of storms that may appear, that elevate the background water level of the Baltic Sea and may appear in 1 year of December, and the same event may continue in next year, January. And to avoid that kind of correlation, we will use another set of maxima over the stormy season, starting from July of 1 year and ending in June of subsequent year. And from this, we construct the ensemble of projections, and these projections we use to construct the ensemble of parameters, and the parameters we apply to construct the ensemble of 40 different projections of extreme water levels and their return periods. And for this we use these 2 different circulation models, different sets of block maxima, these annual and stormy year maxima, and also different methods of calculation of extreme value distributions. And this ensemble we apply to find the estimate of 50-year return period for extreme water level values for our study area along the coastline of Baltic states. And if these block maxima are independent, then they should follow the generalized extreme value distribution. For this distribution, we find three parameters: the location, scale, and shape parameters. And the shape parameter plays a central role in these projections. If the value of the shape parameter is negative, then this generalized extreme value distribution turns to Weibull, the three-parameter Weibull distribution. On the figure, it's a red line, showed with the red line. And Weibull distribution means that projections for the future have slow increase in time. But if the shape parameter of GEV is positive, it indicates the Frechet distribution. Frechet distribution is blue, showed on the figure with blue line. And in this case, the increase of extremes for the higher return period is much more rapid, and many more dangerous floodings may occur. And if the shape parameter is 0, it indicates the Campbell distribution. This is green line, and this is the increase of extremes between two previously mentioned distributions. So if we compare the estimates calculated by different methods for this GIV parameters, for a shape parameter, the scatter is extensive, and this means that the straightforward use of Campbell distribution for extreme water levels is not justified. Usually in our region, in this east coastline of Baltic states, Campbell is most commonly used. And the different estimations for GIV shape parameter in the most of coastal regions do not match well. But the average of these estimations changes its sign several times along the study area, crosses the 0 line. It's maybe not perfectly visible everywhere here, but the average is below 0, negative in the coast of Baltic proper shores on the left side of the figure, and also at the west of the Tallinn until Sõrve. And the average of GIV shape parameter is 0 in most of the areas in Gulf of Riga, except Pärnu region, and also in some points of open shores of West Estonian archipelago and at a part of the northern coast of Estonia. And this parameter is positive in Pärnu and at the end of the Gulf of Finland. And also the match between the estimates calculated based on modeled data and based on the recorded data varies remarkably along the study area. The match is better with recorded data in Latvia than in Estonia. The GIV shape parameter based on one projection, the RCO data, varies substantially along the study area. And here are visible that the points marked with red should follow the Campbell distribution, and there the increase in extreme values in time should be slow, but still existing. And the points marked with blue follow the Frechet distribution, and in these regions the increase in extremes is rapid, maybe rapid, and these are more prone to extensive floodings in the future, these areas. And the points marked with yellow should follow the Weibull distribution, and they show the slowest increase in extreme water levels in time. And the spread of the projections of extreme water levels that would occur once in 50 years is almost constant. It's 40 centimeters along the entire study area. And appropriate projections of extreme water levels can be obtained as a weighted average of the ensemble members. And the resulting return periods are higher in the bayhead, like in Pärnu region, and also in Narva-Jõesuu, in the bayhead of Gulf of Riga, and lower at the open part of the Baltic Sea, at the coast of Lithuania and Latvia and West-Estonian archipelago. And we also watched the GeoShape parameters for the water level minima. And in case of minima, the negative surges are formed slowly, turning high atmospheric pressure and offshore winds, and they persist for a longer time. And because of that, they have a totally different timing of water level maxima. They occur in summer. Therefore, the minima found over stormy season, starting from July until June next year, may be highly correlated and is probably not usable in this case. But as a result, the GeoShape parameter values along shore are mostly negative, and this reflects the presence of three-parameter variable distribution. And this signals that the decrease in the minima is likely the modest. And it is also possible that some regions or coastal sections, some recordings there already are the maximum possible minimum, or possible minimum. And the estimates of different models clearly separate for different groups, two different groups. And to conclude, the nature of extreme water levels may radically vary along the shores of the eastern Baltic Sea. In the eastern parts of Gulf of Finland and Gulf of Riga, the extreme water levels seem to follow fresh sea distribution, and therefore they may exhibit rapid increase in time. In the rest of Gulf of Finland and at the West-Estonian archipelago, the increase is smaller but still existent because of Kumbel distribution. And in the shores of Latvia and Lithuania, the increase of extremes is the slowest because of presence of variable distribution. But this study also indicates that in most of the areas, usage of Kumbel distribution is appropriate to find the extreme water levels in our study area. And for negative values, the three-parameter variable seems to be the most suitable. And also different methods for estimates of the parameters of the general extreme value distributions may lead to considerably different results. Thank you for your attention.
Thank you very much. My first reaction is that what will happen to this maxima in the future? Do you have any opinion about that?
Well, I can only speculate, but probably it will increase.
Yeah. And how should we take this into account, these extreme events in Tallinn, for example?
Well, if making the coastal planning or city planning, these things have to be considered.
Okay.
Also in Pärnu, I think this is the most dangerous region.
Yeah.
Or endangered.
Okay, other questions? Do I see any hands here? Everything is clear with water level for everybody. At least maybe Tarmo has some comments to this. Pena has a comment, yes, thanks.
I have a very interesting comment actually. I have done a lot of ice flow statistics last 40 years. I came to the same conclusion as you, that Kumpel is quite good in some ice load, but viable with 3 parameters is best. So it's interesting. Ice loading and this water level behave the same. Statistics, very interesting. Thank you. The same water, of course. So,
yeah, I do have some comments. So in a way, this seems to be heavy mathematics. But if you take a gymnasium scale pupil and tell how to do that, it's fairly easy, even if it's very scary in some sense. But there are much more deeper consequences, or I would say even ramifications from this analysis. One thing is clear, that in some coastal areas you may feel safe. Whatever maxima you have had, either high water levels or low water levels, there is no potential for increase. So our colleagues in Latvia and Lithuania and Upper Baltic protocol may feel really safe. And some areas, quite limited areas, are such that much higher extremes are expected. Whether it will happen this year or next year or in 10 years, it's debatable, but you shouldn't build close to the coast, no way. This is one thing. Other thing is that different methods for estimates of those extremes give you radically different answers. Which means that if you are going to use some statistical methods, never ever limit yourself to one method. Our experience is that simple thing, estimate of parameters of viable distribution for flow speeds measured by an ADV. If you use maximum likelihood method, you get one result. If you proceed from moments, you get completely different result. The difference is 50%. And if you project that into far future, the difference is absolutely major. So be aware about traps which are provided by single statistical methods. But one more thing which was actually striking, possibly for modelers, we have very few modelers here. The models which we think are almost perfect for the Baltic Sea, they are not. Models mostly which are used for operational modeling, they reproduce kind of moderate water level elevations and depressions really nicely. But most models, I think that even all models which are in operational use today are not able to replicate water level maxima. This is kind of striking message. There is a lot of room for improvement, either models or forcing fields. The RCO model, Rossby Center Ocean model, had very specific forcing fields, and it reproduced almost perfectly maxima in the Eastern Baltic Sea, but failed to reproduce maxima in Western Baltic Sea. And the things are even much worse for water level minima, where we see clear difference in the performance of models, not in terms of, yes, first of all, in terms of statistical parameters, and this shouldn't be this way. So there is a lot of improvement for models still which should be done. So that's actually not a very good message for those who are modeling, but it's a good message saying that there is a lot of research still needed to understand what happens and why minima or maxima are really not replicated.
Thank you. That was like an extra presentation, so